Hello everyone and welcome to day 39 of the Jamb Physics in 40 Days series. This series started just like yesterday and gradually we are winding off gradually. So what we've been able to do so far is we've been able to look at about 38 topics differently from the Jamb Physics curriculum, and this is topic 39, which is Introductory Electronics. So I want to say a big thank you to all of you that has been part of the series from the beginning, checking out each of the topics that we've been discussing and solving multiple problems on them. I want to believe that by now your confidence level is sky high right now because you've really touched a whole lot of topics, and by now you should be able to solve so many questions. Even when you try the past questions, you should be able to solve a lot of them by now. So please, if you have any question whatsoever, please keep them coming. I will still expect more of your questions. You can just drop them in the comment section and we'll definitely attend to all of your questions. And if you're seeing this video for the very first time, well, there's still time. This is Jamb Physics in 40 Days. It's a series that is brought to you by Oya Learn, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you should be able to get all the necessary skills and tools that will help you ace Jamb Physics. So if you're a candidate who is preparing for the next Jamb exams and physics is one of the subjects that you have selected, then these videos are made specifically for you. So trust me, you want to check out all the videos in the series from day one to the end. Like I said, each of the videos we talk about the individual topics that are in the Jamb Physics curriculum. For day one, there's a different topic. For day two, a different topic. As you can see, this is day 39 and we are looking at Introductory Electronics. So you want to look at each of these videos, and what we do is that when we look at the topics, we break them down and tell you what is expected of you as a candidate taking the exams concerning that topic. Then we go on to solve past questions on the topics while we give tips that will help you solve questions like that with great accuracy. So you don't want to miss any of the videos in the series. So what you want to do is ensure that you are subscribed to the channel and also click the notification bell icon so that every time the videos are up, you will be notified. So please do that, and don't forget to like and share the video also because it's our goal to reach a wide range of students that are in need of content like this. So please keep liking the videos, keep sharing them so that we continue to reach many more students. And also, to make your practice even more fun, you can do that with the Exam Fun app. Now, the Exam Fun app is available either on Google Play Store or on Apple Store. But to get it easily, just click the link in the description box of this video, and that will lead you to download the app directly. So once you click the link, you want to download the app and register and then begin to have fun as you learn. And what's even more interesting about the app is that it is also rewarding in the sense that as you score points, you also earn some money. So click the link and download the app today. And if you have any question at all, please put it in the comment section. We will definitely attend to all of your questions. Now, introductory electronics consists of a variety of topics that we have to look at, and what is expected of every candidate by Jamb is listed here. You should be able to tell the differences between metals, semiconductors, and insulators. And what they expect is that you should be able to differentiate them by what is known as band gaps. Now, band gaps refers to the amount of energy that differentiates the valence level from the conduction state. Now, for something to be able to conduct electricity, it's the band gap that determines how well it does that. Like, for example, metals or all conductors in general have no band gap at all. Okay, then when you get to semiconductors, they have a band gap that ranges between 0.1 to about 1.7 EVs. Okay, so that is the band gap for semiconductors. While for insulators have a band gap of greater than 3.0 electron volts. So you see that the more the band gap, the less they conduct electricity. So that is why the best conductors are known as metals, while we have those that have intermediate properties between conductors and insulators. Those ones are called semiconductors. Now, for the study of semiconductors, we limit them majorly to silicon and germanium. So those are the ones we're going to be working with. And then we have insulators like rubber, plastics, and the likes that have the band gap of 3.0 electron volts. Now, another thing that is expected of you is to be able to differentiate between what we know as intrinsic semiconductors and extrinsic semiconductors. Now, when you get a semiconductor like silicon or germanium in its pure state, they are known as intrinsic semiconductors. That is, they are semiconductor materials that has not been, that no impurity at all has been added to them. So they are in their pure state. So that's why we call them intrinsic. Now, when they become unpure, that is, there is a level of impurity in them, they are then called extrinsic. But it's important that I mention this. When we say extrinsic semiconductor, we don't just mean that impurities has been added to the pure semiconductor, but we added a suitable amount of a particular type of impurity. Now, there are two types of impurities that we add. We have what we call the trivalent impurities. These include impurities such as boron, aluminium, and the likes, even indium. Okay, these are trivalent impurities. Then we have the pentavalent impurities. Now, these include things such as arsenic and the likes like that. So these are pentavalent impurities, these are trivalent impurities. Now, let me explain what we mean by this. You see, semiconductors are able to allow electricity to move through them, right? But it depends on whether it has higher number of holes or higher numbers of electrons, because conduction happens in semiconductor either by holes or by electrons. Those are the electron carriers. Okay, so let's note that here, electron carriers, okay, or current carriers. We have holes or electrons. Okay, so for the holes, they are positive, the electrons will take the negative in this case. So when it has more holes, we create what is known as p-type semiconductors. Then when it has more electrons, then it is what we call the n-type semiconductor, where p is positive, n is negative. I believe you understand what that means now. So by the time you had a trivalent impurity, right, because it only has 3 valent electrons, it will mean that you have more holes than electrons in that case. So for that reason, by the time you had a trivalent impurity to it, you have successfully doped the semiconductor to become a p-type semiconductor. Now, it has more conduction, that is, the conductivity is increased because of the introduction of the impurity, okay, and it makes it a p-type semiconductor. Now, on the reverse, if you should dope it with the pentavalent impurities like arsenic, what you'll be getting is an n-type semiconductor because of the excess electron, which will act as charge or current carriers. So when you have excess electrons as charge carriers, you have n-type semiconductors, okay? So, and what I just called dope there is the process by which you add the impurity. So if you're asked to define doping here is addition of what? Addition of impurities. And you shouldn't forget that the purpose of addition of impurities is to increase the conductivity of the semiconductor. Basically, you are making the semiconductor to act more as a conductor now because of the addition of those impurities. And don't forget, you have to choose your type of impurity depending on the type of semiconductor you want to create to be either p-type or n-type by adding trivalent for p-type and then pentavalent for n-type semiconductors. Now, aside that, you should also be able to mention the uses of semiconductors, although we'll come back to this when we talk about diodes and transistors, and then you should be able to differentiate n-type and p-type semiconductors. I've given an explanation on how you can create that using impurities already. and then you should be able to give us give the applications of diodes and transistors, and not just that, also be able to even tell how they are created. Now, for example, the diodes, the common name we use for it, the common diode we have is known as the PN junction diode. Now, there are other types of diodes such as the light emitting diode and the Zener diode, but I will focus a lot on the PN junction diode. And what this means is that you have brought a suitable amount of p-type and n-type semiconductor and then fuse them together to produce what is known as the PN junction diode. Now, it can act as a demodulator, a signal demodulator, but most times it is used in a rectifier circuit. So that is, when you are talking about the applications of diodes, you should be able to talk about rectification. Now, rectification is defined as a process whereby an AC signal is converted into DC. That is, converting AC current to DC current using PN junction diodes. Now, there are two types of rectification. We have what we call the half-wave rectification, where you use just one diode, and then we have what is called the full-wave rectification. Now, the full wave is two. You can either be using two diodes or you use four diodes for the bridge method. Okay? Now, that is for applications of diodes. And then she also talk about the applications of the transistors. Now, transistors, there are two types of transistors. We have the PNP and the NPN. You should be able to differentiate them from their symbol. Now, let me give you the symbol for PNP. Transistors normally are drawn like this, where this is the base. Now, this is collector, this is emitter, but at the emitter, there is usually an arrow. Now, when the arrow is pointing inward like this, you see, when the arrow goes inward, this is PNP transistor. Now, by the time you draw the same thing, remember this is base, this is collector, this is emitter. Now, by the time the arrow is pointing outward here, this is NPN transistor. And just like the name suggests, NPN, PNP, it means you are bringing p-type, n-type, and p-type, n-type, p-type, n-type. You see that now? So that's what leads to transistor. So all of these that we are talking about, you can't find basis for them without first understanding semiconductors and then the p-type and n-type semiconductors. Now, when it comes to the uses of transistors, they are mostly used as fast switches, okay? But they also have other uses such as amplification of signals. Like in your transistor radios, they amplify the signal there. And also the same thing in your machines that we use for sound systems, like your sound amplifiers that you use either in churches or places where sound systems are highly used. Even in your home, there are a lot of sound systems there that make use of transistors in their applications. So they are used to amplify the sound signals that are gotten in there. Now, this is a list of what is expected of you. And there could be a case where I might have missed one or two things while we're talking here. But if you want a full detail, I advise that you check out our video on electronics. It's on the channel. We talk about it in more detail. And on each of these subtopics, we take time to explain them, the process involved, and also solve many questions on them. So that video is more detailed than what we are having here. This is just a crash course to kind of highlight what is expected of you, things that you should look out for, bullet points that you should study when you are taking your readings on Introductory Electronics. So what we'll be doing now is we'll just be moving to solving past questions from Jamb on electronics. But as we are doing that, I'll also be giving you some pointers, things that you should look out for, and also some tips that will help you answer questions on electronics with great accuracy each time you do that. And so please don't forget to follow the video and also give us a like. And if you have any comments, any question at all, please put it in the comment section and we'll definitely attend to all of your comments. So if you're ready now, let's answer some questions on Introductory Electronics. So let's start with this question, which says, in a pure semiconductor, the number of electrons in the conduction band is... Now, remember this statement says pure semiconductor. It could be twisted to say in an intrinsic semiconductor. So intrinsic means pure state semiconductor, okay? So when it is in its pure state, what happens is that the number of holes and electrons are balanced. They are equal to each other, okay? But by the time it becomes extrinsic, now the number of holes and electrons depends on whether it's a p-type or an n-type semiconductor. So if it's a p-type, it will have more holes in the conduction band than in the valence band. And then if it is n-type, it will have more electrons in the conduction band than in the valence band. But this is pure semiconductor. So it's going to have equal in the valence and conduction band. So therefore, this says in a pure semiconductor, the number of electrons in the conduction band is, the answer will be B, which says equal to the number of holes in the valence band. So we go with option B. This question says pure silicon can be converted to a p-type by adding a controlled amount of. Now this tells you that we don't just throw in atoms willy-nilly to dope a semiconductor. It has to be a suitable amount, that is a calculated or controlled amount of impurity. And if you recall, I did mention at the beginning of the videos that we are either adding a trivalent impurity or a pentavalent impurity. So, and I said that the number of holes and electrons is what tells us whether it will become a p-type or an n-type. So if you want p-type, like in the case of this question, you are going to add a trivalent impurity, with examples such as boron, aluminium, indium. But if you want n-type, you would be adding pentavalent impurities such as arsenics and the likes. So for this question, we want p-type, so we go with trivalent impurities, option A. In a semiconductor junction diode, as the depletion layer or barrier layer is forward bias, the layer, now when we say forward bias, it means you have your diode. Remember, this is the positive side of the diode and this is the negative side. So when you connect the positive side to the positive terminal of your cell and the negative terminal to the negative side of the diode. Now what this means is that, remember that a diode actually allows current to flow only in one direction. So when it's forward bias, it will act more as a conductor, allowing current to flow easily. And by the time you draw the VI characteristics graph for forward bias, remember this is forward bias, what you experience is something that goes like this. So it is slower until it gets to the knee junction here, and then it peaks. But by the time you do for reverse bias, the VI characteristics for reverse bias goes like this and then remains constant. It does not allow current to flow again. Now what happens here is this, is that in reverse bias it will act more as an insulator, in the sense that what we are looking at here, which is actually the depletion barrier, will begin to widen. Remember I mentioned that how you can differentiate a metal, a semiconductor and an insulator is by how wide the depletion barrier is. Now in the case of the barrier gap, the band gap for metals, there is no band gap. For semiconductors, it ranges between 0.1 to 1.7 EVs, and then for the insulators it's greater than 3.0 EVs. The same thing happens in barrier layers for PN junction diode. Okay, so in forward bias here, to allow current to flow, because this barrier layer there, the depletion layer, becomes narrow, it's smaller, so it allows currents to flow easily. So you can easily move from the valency band to the conduction band without problem. Okay, but by the time it becomes reverse biased, the same depletion barrier now will be wide, so making it difficult for currents to move from one junction to the other. So since this question is talking about the forward bias part, which means that it is more of a conductor, that means the depletion barrier or depletion layer should be narrow or small. So the option to go for here is therefore B. But don't forget that if it were reverse bias, it will be wide. Okay, so that's the difference, but this one is narrow, so we go with B. This question says the major difference between a pure semiconductor and a pure metal is that, now option A says metals are harder than semiconductors. Now many people easily pick this option but there are a few things that are wrong there. Number one, it is not a major difference between them. So, and because the question says the major difference, even though we can consider it as a difference, it is not the major in this case. And then secondly, there are some semiconductors that are actually harder than metals, like diamond, for example, which is an allotrope of carbon. It is the hardest material, okay, and it is harder than most metals. So that means this statement is also not true, just as much as it is not the major difference. Now, B says, while resistance of metal decrease with temperature, the reverse is the case for semiconductors. Now, this statement is false because when you are dealing with electricity, in fact, we study the factors that determine resistance of conductors, and temperature is one of them, and the relationship is with direct proportionality. That is, the higher the temperature, the more the resistance when it comes to conductors and metals in general. So it means this statement is false. Now, option C says the resistance of metals increase with temperature, which is true. So while for semiconductors, it is the reverse, and which is also true. Because when you increase the temperatures in semiconductors, the electrons move off and it gives room for more charge carriers in terms of holes, which means that it can then conduct better. That is, the resistance is reducing while the conductivity increases. So this is actually true. And then option D says metals have forbidden gaps while semiconductors have not. Now this is false because metals do not have band gaps at all, but semiconductors have band gaps of about 0.1 to 1.7 EVs. So D is wrong, B is wrong, A is wrong. So the correct answer is therefore option C. In a reverse bias junction diode, current flows by. Now, when you configure a PN junction diode in reverse bias, what happens is that the majority carrier are pushed away from the junction. So the only way current moves is through the minority carriers. So, and that is what this question is all about. So we have to pick our answer as the minority carrier. Don't forget that the majority carriers have been pushed away from the junction. So the only thing that allows the small current that it manages to conduct is by the minority carriers, which is in option D. If you're yet to be subscribed to the channel, I'd like you to take a second to click the subscription button. It is important to us that you are subscribed, and that way we are encouraged to continue to make more of content like this. So please click the subscription button, and then you can also hit the notification bell icon so that every time we post a new content, you will be notified. And don't forget that if you have any question at all, you can always put it in the comment section, and we will definitely attend to all of your questions as you put them in the comment section. Now, to attend to this question, this says when impurities are added to semiconductors, the conductivity of the semiconductor. Now, the process of adding impurities, I've already mentioned that, and it is called doping, right? And the purpose of doping is to make a pure semiconductor become extrinsic. So, and what we are doing that for is to actually increase its conductivity, because a pure semiconductor is more or less like an insulator. It does not allow currents to flow, though it is defined as being intermediate of both a conductor and an insulator, but it's more like an insulator when it is in its pure state. But by the addition of a suitable amount of impurity through the process known as doping, you can increase the conductivity of a semiconductor. Now, it doesn't get to the level of a conductor, but it is closer to a conductor now than it was before. So, so therefore, to answer this question, the answer is just to increase it. We add impurities to increase the conductivity of a semiconductor. So we go with option B. In the circuit diagram of a transistor above, the terminals P, Q, and R represent. Now, this is the circuit diagram or circuit symbol for a transistor. Now, you see this line that comes to this part here is known as the base. Okay, why these two are emitter and collector respectively. Now, how you recognize the emitter from the collector is there's usually an arrow. Now, that arrow will tell you whether it's PNP or NPN. So because there's an arrow here, this is where we call the emitter, while the other part is the collector. Now, bonus point. When the arrow is pointing inward, you have a PNP transistor. And when the arrow is pointing outward, then it is a NPN transistor. So that means this one is what? A PNP. The arrow is pointing inward. So don't forget base, collector, emitter. But we have to arrange it in terms of P, Q, and R. So P is what? Emitter. Q is base. And then R is collector. So emitter, base, and collector. So let's look for the option for that. Emitter, base, and collector. That's option A. The theory of electronic conduction in solids, which satisfactorily explains the properties of conductors, insulators, and semiconductors, is now option A says string theory. Now, string theory is a physics theory that is attempting to explain or unify the all fundamental forces. It's trying to unify all the fundamental forces. So it does not talk about anything in solid state physics and does not talk about how conductors, insulators, and semiconductors behave. Now, for particle theory, this one is explaining how that all materials or all substances in matter are made up of tiny particles known as molecules, right? And then C is group theory, which is also a mathematical attempt to explain symmetry, okay? But D, which is band theory, is what explains how band gaps can differentiate between conductors, insulators, and semiconductors. So therefore, the answer to this is option D. A certain manufacturer wishes to make an N-type semiconductor. Which material would he select for doping? Now, it needs pentavalent atoms to dope the semiconductor to make it N-type. Remember that for P-type, you need trivalent, that is group 3 atoms such as boron, indium, aluminum. Those are group 3 atoms that can produce P-type. So for N-type, you need group 5 atoms such as one of them being arsenic, another being phosphorus, another being antimony, and then there is the case for bismuth also. These are group 5 atoms that can produce the N-type semiconductor. So we just have to look for an option that has 2 of them at least. So here we have boron and antimony. Antimony will work, but boron will not. Boron is for P-type. This is also boron, so P-type cancels out the phosphorus here. C says aluminum and indium, which is for P-type. Both of them will produce P-type. But D says arsenic and antimony. And arsenic and antimony produces N-type semiconductor. So that will be our answer, option D. A p-n junction diode is used as, now one of the uses of a p-n junction diode is as a rectifier. That is, it is meant to convert AC into DC. Okay, but here we see rectification and then we see amplification. So for amplifiers, you would need a transistor. But for rectifiers, you need a p-n junction diode. Now, when we consider the options where we have rectifier, option A says a rectifier in a DC circuit and D says a rectifier in an AC circuit. And don't forget that rectifier means something that converts AC to DC. So you wouldn't want a rectifier in a DC circuit because there's no AC to convert to DC there. Just putting it there will just act as a conductor in that DC circuit. But you need a rectifier in an AC circuit so that you can convert that AC current to DC. So the answer here is D. If you're yet to be subscribed to the channel, I would like to implore you to please take a moment of your time to click the subscription button. And please, if you have any question at all, don't hesitate to put it in the comment section and we promise to attend to all of your comments. And please keep liking the videos and keep sharing so that you can help us to reach a wide range of people who are in need of videos like this. Now, this question says transistors are used for. Now, in the last question, I did answer this, so you can take a moment to answer this question. So I believe that your answer also would be that it is used to amplify signals, and that is in option C. So put our answer as C. In semiconductor, the carriers of current at room temperature are, now for semiconductors, what carries current, or what we call the current carriers or charge carriers, are holes and electrons. Now, the only thing is that in some cases, like in p-type semiconductor, we say that the holes are the majority charge carriers, while for n-type, the electrons become the majority charge carriers. Now, the fact that we have majority charge carriers and minority charge carriers does not mean that they don't carry charge still. So it still means that both the holes and electrons are regarded as charge carriers. So the answer to this question is then option B. Now, you can practice with many more questions like this. You'll find them on the Exam Fun app. It is a very interesting app that infuses fun into your learning time, where you get to answer questions on any subject of your choice at different levels while scoring points and also earning some money. So you can download that app by clicking the link in the description box of this video, and please leave us a comment with any question at all you have concerning what we're doing, or if it's something you found during your study time that you need some help with. Please don't forget to subscribe if you haven't done that already. You can subscribe by clicking the subscribe button on your interface there, and you can also hit the notification bell icon so that you get alerted every time we post a new content. So let me say a big thank you to you for following the series so far. This brings us to the end of day 39. The next video will be for day 40, which will be ending the series. I hope to see you then. So bye for now.